In this video, we'll be talking all about sensor calibration. And in sensor calibration, we're basically wanting to compare one instrument, the instrument that we want to calibrate, with a standard, an instrument that is highly accurate. And we want to put the same signals in each of them and see what the output we get from each of them is. Once we've seen what the output is, we can compare those and adjust our actual sensor or measurement system to what the calibrated value should be. Once we've done that, we've essentially calibrated our system. So we have a series of set inputs that we'll have. We'll expose these to our measurement system and our standard and compare the two of them. Essentially, we want to do this over the range of measurement that we're dealing with, because maybe our sensor's non-linear or something about our sensor's non-linear. We want to test this over the entire range that we're dealing with, and not just two values. We want to test multiple values so we can characterize it well. It's also helpful to calibrate or understand the sort of effects that we get over different temperature conditions or different environmental conditions. Those environmental conditions, whether it be temperature or pressure, for example, will affect our performance of our calibration and how well the sensor is going to reproduce as a measurement output what the actual value is. Now, for example, springs change their elasticity based on the temperature. Also, the speed of sound changes with temperature and pressure. And so if we're using a sonar that bounces signals off something to measure the distance between them and uses the time of flight principle, based on how quickly that sound's going to be traveling, based on the temperature and pressure, environmental conditions, based on how accurate that calibration for our sensor actually is. Now, typically our standards at a greater level of precision and accuracy than the thing that's under test. And we only use our standards as standards. We don't use them in the lab every day and check everything. They'll probably go out of standard if we do that. And we use our standards as our golden ruler, or our thing that we line up our sensors against or our measurement systems against and test them and work out if they're accurate or how accurate they actually are. Now, a lot of instruments that we use, a multimeter, a pH meter, or whatever it may be, will be calibrated, for example, at the factory. But we don't just calibrate them at the factory, we often need to recalibrate them over time. Because things related to the environment or how they're used, how often they're used, wear and tear, dirt that gets into them, that will change our calibration over time. And so we might need to maybe annually or more often recalibrate our sensors. When we're doing calibration, we've got that standard equipment that we're using, so the calibration standard. We calibrate it in the prescribed conditions that the standard dictates. We have a standard procedure that we operate on, and we have trained operators that can calibrate things to a particular standard. And so this calibration procedure is very standards driven. Here's the procedure you follow, here's how you do it, here's the conditions you do it under, and you end up getting the results, and you end up getting something that's being calibrated. Now, there's a bit of hierarchy of calibration standards. At the bottom there, we have the process instrument, the thing that we want to calibrate, the thing that we want to actually get more accurate. We then have a working standard, and the working standard is something that we might have in a lab to actually calibrate our instrument against. It might be a super accurate multimeter, for example, or it might be something that we can use with our buffers for measuring pH. We might have a standard that is, this is pH 7 exactly, and this is pH 9 exactly, and this is pH 3 exactly, or whatever it may be. Something that is a standard we can measure it against. We then, upper level, we have our secondary standard, which is a calibration facility that might be accredited by someone like NASA, and they actually are the ones that specify the working standards or calibrate the working standards for us. Above them, we have national standards organizations, and there's quite a few of them. There's the ISO International Standards Organization, there's Standards Australia, there's NADA, that can calibrate or prescribe for our secondary standards. And then sitting above that, well, essentially we have our definitions of units, of what is a volt, for example, or what is an ohm. There are SI definitions that we talked about last week. Now, lots of systems also have a startup calibration. When we turn a set of scales on, for example, it'll often calibrate it saying, okay, we're assuming that nothing's on the set of scales at the moment. What's the weight at 0? And we can then say, okay, we've got nothing on there. We can reset it to 0. Something with scales, for example, we can also have a tear button. And I use this when I'm, for example, doing cooking or making pizza dough or something like that. You add in your mixture of water, how much water you need for your pizza dough. I think it's 337 grams or mils. They're actually the same thing when you're talking about water. And then you press tare and it will reset to 0. And then you can add your other things like your flour and how much flour do you need for this particular recipe. And so there are startup calibration and, well, basically an in-use extra calibration. Another place this startup calibration is actually used is with gyroscopes and accelerometers for little drones and things like that. You basically need to put on a level surface to begin with and leave it for 5 seconds, and it learns what its level position is. It calibrates that sensor for a level position, and then when you use it, it knows where it started off as a level position, and that will be fine for maybe 10, 15, 20 minutes, whatever it may be, depending on the quality of the sensors. One thing that might be helpful is clarifying calibration versus characterization. Because often, and like for the labs that we're dealing with in this particular subject, we don't need finely tuned calibration to, let's talk temperature for a moment, to 1,000th of a degree Celsius. It's not really going to matter so much for the purpose of our labs and for the experimentation that we're trying to do within this class. And that's good because specialized calibration is expensive. It needs special equipment. Now, many applications require less specialized calibration. Here we're trying to calibrate, well, more characterize what the performance of the sensor is going to be. And so it might matter in terms of temperature to be accurate to 1 degree Celsius or 0.1 degrees Celsius rather than the 0.001 degrees Celsius. And so for a linear sensor or a sensor that's fairly linear, the way we do it is essentially we do it very much like you do your normal calibration, but to a lesser degree, to a less stringent degree. So if we're doing a temperature sensor, we might get like a multimeter with a thermocouple and do a series of measurements at different temperatures. We might have a room or a cup of water that's 10 degrees and one that's 20 degrees, one that's 30 degrees and 40 degrees, and measure with our multimeter, measure what that is and what our recorded temperature is, and measure with our sensor, whatever sensor we have. And we can then take it into Excel or MATLAB or something like that, draw our straight line through them, and we've characterized our data. Likewise, we could do that with a different sensor, like a strain gauge, for example. We could have a series of set weights going up by maybe 50 grams or so. We can measure them with our set of scales. Then we can put them on our strain gauge when we're measuring our beam deflection or something like that, and use that as our standard for calibrating and characterizing the particular sensor we're working with.